All right, so this week we'll be taking a look at section 6.5. We'll split that into 2 days, and part of section 7.2. It's not the best place to stop because we're going to be halfway through a section and we're not going to get back to it for a while. So when we do get back to it, we'll have to review a little bit. All right, so we're going to be looking at trig functions. Okay, so we're going to look at like sine, cosine, tangent, secant, cosecant, and cotangent. But we're going to be doing it in what's called a right triangle. Okay, you don't have to use a right triangle to do trig, but if you do, it does make some things a little easier. So if I have a right triangle, what does that mean is special about it? Jane?
It has a 90-degree angle.
Right, it has a 90-degree angle in it. Right. So every triangle that we deal with in this section has a 90-degree angle. When we get into like a problem, let's say I wanted you to calculate the angle that the Tower of Pisa is leaning at. Well, what happens there is you've got the ground, you've got a tower that's on a slight angle. So what we can do is we can make a triangle out of it, but it ends up being a triangle something like that. This angle that I just marked x isn't a 90 because the tower is leaning and it's not perpendicular to the ground. All right. So for now, we'll stay away from those kinds of triangles. So if we have a 90, then the side opposite that has a special name. Okay, it's the longest side. What's the name of that side? Yep.
The hypotenuse.
The hypotenuse. And what about the two other sides? Does anyone remember what those are called? Two.
Opposite and adjacent.
Okay, so that is one name for them, depending on the perspective in the triangle. One would be opposite and one would be adjacent. Does anyone know another term for them? The two
Aren't they called legs?
legs, yeah. One of the legs is the opposite, one of the legs is adjacent. Which one is which depends on your perspective. Okay, so here's a diagram of what we just said. So I've labeled the right angle. I've marked another acute angle in the triangle. We'll talk more about acute angles in a bit, but in general, an acute angle is just an angle between 0 and 90. I've labeled the sides the way we often do in the Pythagorean theorem, ABC. So when we label triangles and we don't know anything, generally the sides are labeled with English letters ABC. When we label angles, we use Greek letters. Sometimes we use theta, like I did there. Sometimes we're going to use alpha and beta as well. Okay, any questions on the labels in that picture? We're going to touch on this more later, but why does that angle have to be acute? Why does it have to be between 0 and 90? And so does the one at the top. How come? Tim?
Because the two of them have to add up to 90.
And why do those two have to add up? Why does this angle and this angle have to add up to 90?
Because if the other one's already 90, then all three of them have to equal 180.
Yes, so the sum of all the angles in a triangle is 180, and that's the key. Okay, if you know that, then that proves that the other two have to be acute, because if they weren't, if one of them was more than 90, and you already have a 90, well then it would add up to more than 180, and that wouldn't be a triangle. At least it wouldn't be a two-dimensional, flat, Cartesian triangle. There are triangles that the angles add up to more than 180, but they're not flat. They're like a spherical triangle. And if you think about like connect the North Pole, Boston, and London. If you connect those 3 points, you get a triangle. But it's a triangle on the surface of the Earth. It's curved. So the angles in that type of triangle don't necessarily add up to 180. We're not dealing with anything spherical. Everything we do in trig is Cartesian based. Okay. Flat. All right, so Pythagorean theorem. Sometime if we have time, maybe today or tomorrow, I'll go through a proof of why that theorem is true. Well, maybe we've got a little time. We could do it. Okay, there's many ways to prove this theorem. There's probably 40 or 50 different ways, maybe more. One way that I like to do it involves a picture, okay? And basically looking at area. So let's take a look at this picture. So what I've drawn is a square, kind of rotated a little bit. All the sides of the square are c units long. And then you can kind of think of on each side of that square I've attached a triangle. And that makes a larger square. Any questions on that diagram? Okay, so what we want to do is we want to focus on finding areas. Okay? And I want to find the area of something in that picture, but I want to find it two different ways. All right, let's focus on the area of the big square. How do you find the area of the square? What's the formula? Leo?
Side square.
A side square. And what's the length of the side of the big square?
A plus B.
It's a plus b. So, area of big square equals a plus b squared. All right. Now I want to focus on finding the area a different way, kind of by looking at the individual pieces that make up that big square and doing it that way. Can somebody tell me what shapes make up that big square? What do we have for shapes that make up that big square? Gracie?
4 triangles in a square.
We have 4 triangles in a square. So let's find the area of one of those triangles because they're all the same. They're all congruent, all 4 of the triangles she just mentioned. And then we have the small square in the middle. All right, so we'll call this the first way to find the area of the big square. Second way. Dylan, what's the area of the small square?
C squared.
Yep, c squared. Plus, we have 4 of those triangles. So 4. Now I need the area of the triangle. How about, Tessa, what's the area of a triangle?
This one?
Just in general. Yeah, 1/2 base times height. So for this one, we start with 1/2. And let's look at this triangle right here. You could look at it either way. The base is A, and the height is B. It doesn't really matter either way. So it's 1/2 AB. Okay, and I think we can simplify the second expression a little bit. What's 4 times 1/2 AB? Yep.
2AB.
2AB. So we get c squared plus 2AB. So that's a formula for the area of the big square. That's a formula for the area of the big square. So if box 1 and box 2 are both formulas for the same shape, what does that mean about what's in box 1 and what's in box 2? Yeah,
They're equal.
they're equal. Box 1 and box 2 are equal to each other. So let's write that down. Box 1 equals box 2. Okay, so FOIL out the left-hand side. You get a squared plus 2ab plus b squared. And then on the right, get c squared plus 2ab. Anything I can subtract from both sides? Yeah? I can subtract 2ab. That's gone. Subtract 2ab. That's gone. And look what I'm left with. A squared plus b squared equals c squared. So that's one of probably, again, dozens of proofs of the Pythagorean theorem. And of course, A, B, and C, you've got to look at that carefully. A and B were legs in my picture, and C was the hypotenuse of the small triangle. So you could have used any letters you want to prove it, but I used the letters that we normally use, A, B, and C. Okay. Questions on that? So not too bad. All right, so we've looked at the 6 trig functions before in terms of a unit circle. We said before sine was y, cosine was x, tangent was y over x. Well, now we're going to define them in a similar, but looking at it using different terms. What's y we're now going to call opposite. What's x we're going to call adjacent. And if you're kind of wondering how that works, let's think back to when we had a unit circle. We've got a point on the circle. That side is x. That side is y. And the hypotenuse in a unit circle was always how long? It was always 1. Okay, I'm not really worried about the hypotenuse here. We could just call it r. It's the radius of my circle. So when we did this, if r was 1, then sine would be just y. But if it wasn't 1, sine would be y over r. Cosine was x over r. And tangent was y over x. Those are definitions we had when we did unit circle trig. And then to get the other 3, the cosecant, the secant, and the cotangent, what did we do with those? Yeah, you just flip them. So your cosecant is r over y, your secant r over x, your cotangent x over y. Okay, well, let's just look at those 3. Well, now, if we look at it from the perspective of standing right there, the side that is furthest away from us is the opposite side. It's the side that it doesn't touch the angle at all. In fact, if I got rid of that side, I'd still have an angle right there. Okay? Opposite is the side furthest away. Adjacent is the side that's right next to the angle that's not the hypotenuse. Adjacent is the side that if you got rid of it, look what happened. You don't have an angle there anymore. You just lost one side of your angle. Okay? And then this, you can think of it as a radius, but really it's a hypotenuse in a right triangle. So now we're just going to substitute in the 3 words I have in parentheses in place of x, y, and r. So now sine is going to be opposite over hypotenuse. Cosine is going to be adjacent over the hypotenuse. And tangent is going to be opposite over adjacent. So it's really not that much different than what we did with unit circle trig. It's just using different terms. That's all. Okay, and of course, the other 3 we already said. Take the 3 that you have and flip them. The 3 on the left are the most used. Those are more important. The 3 on the right, we don't really use as much. I think one of the main reasons for that is because if you look at a calculator, you have buttons on the calculator for the 3 on the left. You don't have buttons for the ones on the right. Doesn't mean you can't do it on the calculator, but it's more, well, a few more steps. And now, when we talk about the terms opposite and adjacent, they are relative terms. That's how I describe them. Does anybody know what I mean by that? A relative term? Yeah?
It's relative to the angle that you're using.
Exactly. It's relative to the angle in the diagram. It's kind of like using the words left and right. Right? If you tell somebody to go left, well, it depends on their perspective. If you said in this room, which way is left? Depends which way you're facing. Versus an absolute term, like the hypotenuse is always the hypotenuse. It's across from the 90. That never changes. So an example of that would be asking people in this room which way is up. It doesn't matter which way you're facing. Up is always towards the ceiling. But left and right, it matters which way you're facing. Okay? So that's how opposite and adjacent are. It matters which way you're facing. So in this diagram, if you're standing where theta is, opposite is the side you're looking out at, adjacent is the side that's right next to you. If you were up here, let's call that alpha. Now, opposite is still the side that's furthest away from you, but that would become the bottom side. Adjacent is the side that's next to you. Okay. So one thing I want to look at is when I ask you to find the sine or the cosine or the tangent of an angle, does it matter what size triangle you're using? Because all of these definitions have to do with the size of the triangle. The opposite means the length of the opposite side divided by the length of the hypotenuse. Cosine means the length of the adjacent divided by the length of the hypotenuse. Well, if I said to you, I want to find the sine of 60 degrees, somebody might draw a really, really small 60-degree triangle. Somebody might draw a big one. So the question is, are we going to get different answers for the sine of 60 if somebody draws a small triangle versus a bigger triangle? So let's look at that. So let's say you sketch a 30, 60, 90 triangle. If people were to sketch a 30, 60, 90 triangle accurately, measure it out or use a protractor and sketch it accurate, not everybody's triangle would be congruent necessarily, but they would all be something else. Yeah? They would all be similar. They would all be similar. So what does that mean in geometry? If you have two shapes that are similar, how does that mean they relate to each other? If you had to explain that a little more precisely, they're similar, yeah?
They could be different sizes, but they're proportional.
Yeah, they're proportional. One is either an enlargement or a reduction of the other. That's all. It's a bigger or smaller version, but they're proportional. That's the key. So because they're proportional, if I asked you to find the sine of 60, and you sketch a triangle that's like feet big, and then somebody else sketches one that's only centimeters big, you're going to get the same answer. All right, so let's look at an example with two 30, 60, 90 triangles. These are drawn accurate, perfectly to scale. At least in relation to each other. I'm not saying if you measure that angle, it would come out exactly 60. But these triangles are similar triangles. Okay, and the side lengths are correct for a 30, 60, 90. At least for these particular two. All right, so let's find the sine of 30 using the triangle on the left. Dylan, what did I say that sine was equal to? It's what over what?
Opposite over hypotenuse.
Opposite over hypotenuse. So Sam, in this case, what side is opposite the 30?
The one.
And the hypotenuse?
2.
2. So using the triangle on the left, the sine of a 30-degree angle comes out to 1/2. There's really no unit on that 1/2. It's just the number 1/2. It's not 1/2 inches, it's just 1/2. No unit. Okay, let's do it over here. Sine of 30 degrees. So now we take opposite over hypotenuse. Juliet, what side is opposite the 30 here? And the hypotenuse? Yeah, so we do get the same thing. So if there's a problem where they ask you to find either a sine, a cosine, or a tangent, any of the trig functions, and they ask you to do it for a 30 or a 60, you could do it either way. Okay? They wouldn't ask you to do it for any angles except 30, 45, and 60 by hand. If they ask you to do it for like 57 degrees, that's kind of hard to do by hand. You really need a calculator. But 30, 60, and 45, you should be able to do by hand, generating your own sketch. So the thing to remember in a 30, 60, 90 is the hypotenuse is always double the short leg. If you remember that, then you can sketch a 30, 60, 90 triangle. You just use the Pythagorean theorem to find the third side. So the hypotenuse is always double the short leg in a 30, 60, 90. So the simplest one I think you can draw is right here. That's as small as you can make the short leg and the hypotenuse without running into fractions. If you made the hypotenuse 1, then the short leg would be 1/2. You could do that, but now you got fractions involved. All right, so let's say they gave you a problem like this. I'm going to tell you that the sine of some mystery angle is 5/6. I'm never going to tell you what the angle is. I'm just telling you something about it. It has a sine of 5/6. Find every other trig function. Does anybody know how you would do that? Before I tell you the steps. Think about if the sine equals 5/6. What are they telling you? Yeah.
The opposite and hypotenuse.
They're telling you the length of the opposite side, and they're telling you the length of the hypotenuse. Well, if they tell you 2 out of 3 of the sides, you can always get the third side using Pythagorean theorem. Once you have all 3 sides, you can do any one of these you want. Opposite, adjacent, hypotenuse. Okay? So it's basically the steps. So if you get that, you don't really need to write this down. If you don't, then I would write it down. So take what you're given and recognize that that is 2 sides of the triangle. In this case, the opposite is going to be 5, the hypotenuse is going to be 6. Use the Pythagorean theorem to get the third side using that information. And at this point, you know all the sides in the triangle, so you can find anything you want. We will practice finding all 6. In general, though, bless you, the sine, the cosine, and the tangent are the most important ones. In fact, in trig, you can really do everything with just sine and cosine. You don't need tangent, secant, cosecant, or cotangent. You can do everything in trig with just sines and cosines. If you want to get somewhat picky, you could really do everything in trig with just sine, if you wanted to, everything. But it is nice to have the cosine and tangent because it makes writing things down a little easier. A little bit more concise. All right, so they're telling us we have an acute angle in a right triangle. You can assume that. It has to be a right triangle because There's no such thing as hypotenuse without a right triangle. So if this wasn't a right triangle, we wouldn't really know how to solve this. So find the values of all the trig functions. Okay, so find all of those. As we do this, we're never actually going to find theta. We're never going to know how big the angle is we're working with in the problem. Which is kind of weird because you're going to say a bunch of things about the angle, but you're never going to know the size of it. And kind of an analogy to that is like meeting somebody on the street and describing a bunch of things about them. What color their eyes are, how tall they are, their hair color, what color shoes they're wearing. You're just describing a bunch of things about them, but you don't even know their name. That's kind of what we're doing here. We're going to describe a bunch of things about theta, but we're never going to know its size. And we don't need to. Okay, so in your triangle, it doesn't matter where you put theta. You can put it at the top, or you could put it in the lower right. You're going to get all the same answers. Okay, so Trevor, what because they gave me the function sine, what two sides do I know?
Opposite and hypotenuse.
I know the opposite. I know the hypotenuse. Now, if all I wanted was cosecant, I could do that one pretty quick. Cosecant doesn't involve adjacent. Everything else does. So I can't do anything else until I get the adjacent side. So Rebecca, how would I get the adjacent side here?
Use the Pythagorean theorem.
And can you set up the Pythagorean theorem? You could call this A if you want.
A squared plus 5 squared equals 6 squared.
So we're going to get A squared equals 36 minus 25. So A squared equals 11. So that means A would be, how do we get rid of the square? Oh, crazy? Yep, take the square root. So I'm going to call it square root of 11. Generally, when you do these kinds of problems where you're finding trig ratios, you don't do any decimals. Okay. So now let's go through and do our cosine. Jane, what would my cosine be?
Square root of 11 over 6.
Yep. And Leo, my tangent?
Tangent would be 5 over square root of 11.
Yep. And can you fix that for me so we don't have the square root in the bottom?
Isn't it you multiply both top line by 11 or square root of 11?
Multiply top and bottom by square root of 11, yes. And what would you get if you do that?
5 square root of 11.
Exactly. 5 square root of 11 over 11. Okay, so now let's do our secant. Can somebody tell me what the secant would be at final answer? No root in the bottom. Yep.
It'd be 6 square root of 11 over 11.
Yep. And now for the cotangent, you have a choice. You could flip two things. You could flip what I circled, or we could go back to the original. I would use the original because then the root goes to the top. Any one of those 6 pieces of information is enough to figure out how big is that angle. Is it 37 degrees? Is it 56.2? How big is it? Okay. You could give me any one of those and I could figure it out with it. We'll talk more about that later. Okay. Any questions on that? All right. Let's why don't you take a second and see if you can do all 6 trig functions for this triangle. Okay, a little different than the last one. The last one I gave you the hypotenuse and a leg. This time I'm giving you a leg and a leg. So when you use Pythagorean theorem, put it in the right spot. So let's take a look. Before I can find the 6 trig functions, I'm missing the hypotenuse, so we got to get that first. What did we get for the hypotenuse here? Yeah, Julia? 13, yep. It's a 5, 12, 13. It's a special name for that. 3, 4, 5 is another one that falls into this category. Does anybody know what kind of triangle that's called? Or the numbers that make up the side lengths? Yeah.
Pythagorean triple.
Yeah, it's a Pythagorean triple when all the side lengths are integers. There's an infinite amount of Pythagorean triples. 3, 4, 5 is a common one, 5, 12, 13, but there's infinitely many. And when I say infinitely many, I mean infinitely different types. Like if you said 3, 4, 5, and then 30, 40, 50, that's the same thing. I mean, there's infinitely many types that are dissimilar. Okay, not just larger and smaller versions of the same thing. All right, so now let's go through our functions. All right, so we've got theta is in the lower right, so that's our perspective. Sam, what would the sine be?
Sine is the opposite over hypotenuse. Yeah,
Mhm.
so it would be 5 over 13.
So we get 5 over 13. Yep. Trevor, my cosine?
12 over 13.
12 over 13 is perfect. Leave these as fractions. Don't divide that out. And the last one, my tangent, Tessa? 5 over 12. All right. So now, how about Tanya, to get each of the other 3, what am I going to do with those? Just flip them. So the cosecant of the angle that I don't know is 13/5. The secant of some angle that, again, I don't know is 13/12. And the cotangent of that angle is 12/5. A question like that would be 6 separate things on a test. I wouldn't have you do all 6 in the same question. Okay. Any concerns, any thoughts on that one? Okay, so this one says, use the diagram below to find the 6 trig functions of 45. Well, let's even pretend we didn't have anything labeled. So if it wasn't labeled, you would have to sketch your own 45, 45, 90 right triangle with accurate side lengths. Okay, first of all, does it matter how big or small you make your 45, 45, 90? Trevor?
No.
No, you can make it any size you want, but it has to be similar to every other 45, 45, 90. It's got to be the correct side lengths. So if we label these as my 45s, what else do you know is true in a 45, 45, 90 triangle besides the 2 angles that I put in being the same? Yeah?
Are the legs congruent?
Yeah, the legs are congruent. So pick a number that you want for the leg, any number, but pick the same number for the other leg. So what would be the easiest number to use for the legs? So it's not too much like arithmetic we have to deal with.
1.
Yeah, if you make them both 1, now use Pythagorean theorem, and there's your hypotenuse. Okay, so that's the trick with a 45, 45, 90. If you have to sketch one yourself, just make the legs congruent. The trick with the 30, 60, 90, the hypotenuse is double the short leg. Okay, so now you know the tricks for sketching each type of triangle to scale. All right, now they want to know the 6 trig functions of 45. Does it matter which 45-degree angle I use as my perspective? What do you think, Rebecca? No, because the sides, it's the same. If you use the top 45, the opposite is 1. If you use the bottom 45, the opposite is 1. It's going to come out the same. Okay, so let's go through our 6 trig functions. All right, so let's start with our sine. Dylan, what's my sine here?
1 square root of 2.
Let's see. Oh, okay. So yeah, I'll be 1 over the square root of 2, and then when you fix it, it wouldn't be 1 times the square root of 2. If you have 1 over the square root of 2 and you multiply top and bottom by square root of 2, what would you get?
It would be square root of 2 over 2.
Square root of 2 divided by 2. Yep. And Gracie, what about the cosine?
Square root of 2 over 2.
Yeah, it's the same thing. Because opposite and adjacent are the same thing. And Sam, what about my tangent?
Oh,
Yeah.
Okay. It would be 1 over the square root of 2.
So what's our definition for tangent? It's what?
Oh, it would just be 1 over 1.
It's 1 over 1, opposite over adjacent, which is 1 over 1. So that makes the cotangent pretty quick, because if you flip 1 over 1, you get 1 over 1. Jay, and how about the cosecant?
It would just be square root of 2.
Right, if you flip what you have for the sine and you fix it, you're going to end up with square root of 2. And since sine and cosine are the same, so are cosecant and secant. Okay. Any questions on finding the 6 trig functions for a 45? Okay, and if you're thinking, well, what happens if I make my 45, 45, 90 bigger? It wouldn't matter. If you reduce it and simplify everything, you're going to get the same answers. All right, so now they want us to use this diagram to find 12 things. The 6 trig functions of 30, and then the 6 trig functions of 60. All right, let's just start out by looking at that diagram, because this diagram is not a 30, 60, 90 right triangle. Somehow we're going to turn it into one. But let's start just by looking at what we've got. So Abby, what kind of triangle do we have there?
Equilateral.
Equilateral, because all the sides are the same. Can somebody tell me something else that we would know because that's an equilateral triangle? Yep.
Angular.
It's equiangular. And what does that mean? Can you give me something numeric because of that fact?
They're all 60 degrees.
All the angles are 60. So we've got a 60, 60, 60. Okay. But I still don't have a 30, 60, 90 right triangle. I have to create that somehow. But how could I create a 30, 60, 90 out of that picture? Yeah.
Like split it in half.
Like that?
Like vertically.
Yeah, why don't we go vertically instead of horizontally? So if we do that and just move that over, we can go through the proof, but basically in an equilateral triangle, if you draw an altitude from a vertex perpendicular, because it's an altitude, to the base, you automatically bisect not only the angle, but you've also bisected the side. So let's make a copy of this left-hand side and then slide it over so we can work with it. So it's a little less messy. All right, so we know this side is 2. How about the bottom side? The other leg, it would be how long? Yep, that would be 1. This angle in the lower left, we didn't do anything to it, it's 60. So that means the angle up at the top has to be 30. Even if you didn't know the theorem about bisecting the angle, all the angles have to add to 180. So you've just created a 30, 60, 90 right triangle. The only thing we need is the other side. So there is a trick for finding the long leg. The trick I gave you was the hypotenuse is double the short leg. Well, yeah. So we already have that fact. So unless you know the trick for finding the long leg in your head, how would you get the long leg here? Yep.
1 squared plus b squared equals 2 squared.
Yeah. And it's the square root of 3. Okay, so now we've got our diagram. Let's find the trig functions. This time, I'm not really interested in the numbers that you're going to get because I'm sure everybody has a good idea of how to find the sine and the cosine. I'm interested in looking at a pattern that happens between when you find the 6 answers for 30 and then the 6 answers for 60. All right. So let's take a second and see if you can figure out the 6 answers you get for 30 and then do the 6 answers you get for 60. And I want to look for a pattern. All right, so let's go through and see what we got for the trig functions for 30. Okay, Tanya, what did you get for the sine of 30? 1/2. Rebecca, cosine of 30?
Square root of 3 over 2.
Yep. And Tessa, the tangent of 30? Square root of what? Square root of 3 over 3. Yep. Now we're going to flip them all. So your cosecant is 2. Your secant, 2 root 3 over 3. And your cotangent, root 3. Okay, now let's go to the 60 and see what happens. Dylan, what'd you get for the sine of 60?
Square root of 3 over 2.
Yep. And Gracie, the cosine of 60? 1/2. And the tangent of 60? How many people got root 3 for that? Yep. All right. Cosecant? Sam, what's the cosecant of 60?
2 squared root 3 over 3.
2 root 3 over 3. Your secant is going to be 2. And your cotangent, root 3 over 3. Okay, so now looking at those numbers, does anybody see a pattern? Sam?
The sine and cosine switch.
Okay, so let's just kind of put a box around that. So those 2 answers switched places. The sine and the cosine. Sine, cosine. Okay. What else? Yeah?
The tangent and cotangent changed.
Yep. The tangent switched places with the cotangent. Tangent, cotangent. Okay. And then the last 2 that switched places, secant, cosecant. So the way I pronounce them, hopefully you're kind of picking up on the hint there. These functions switch places, are called co-functions. Sine, cosine, that's one group. Secant, cosecant, that's another group. Tangent, cotangent. Those are your 3 pairs of co-functions. And the other thing to notice is look at the argument. 30, 60. If you add those together, you get 90. Does anybody remember what that is called when you add 2 angles together and they add up to 90? Yeah?
Complementary.
They're complementary. Right? So I'm going to argue that the 2 acute angles in a right triangle are always complementary. Why? Why do the 2 small angles in a right triangle always have to be complementary?
Because if there's already a 90-degree
right triangle, the other two have to add up to 180 because their triangle is has 180 degrees.
So the other two have to add up to 90. Okay, yeah. So yeah, you have a right triangle, you've already used up 90, so the other two have to add up to 90, which means they're complementary. Okay, so that's important. Two acute angles in a right triangle are always complements. Okay, let's look at this. So what I've done here is I just labeled the generic right triangle, sides A, B, and C. Our book uses capital letters for angles and lowercase letters for sides. I'm not going to do it that way. I think that gets confusing. Because if you're starting to use capital letters for one thing and lowercase letters for another thing, well, depending on the letters you pick, a capital and a lowercase can look the same. Think of like the letter C. They look the same. So that's going to be confusing. So we're not going to do that. And the other thing is, if you ask me a question like, you know, what's X? I'd have to say, well, do you mean capital X or do you mean lowercase x? What are you talking about? So if we use Greek letters for angles and we use English letters for sides, then there's no question what we're talking about. Okay, so in this picture, I want to find something. Let's find the sine. Let's pick an angle. Doesn't matter. The sine of alpha. Someone tell me what the sine of alpha would come out to there, Jane?
A over C.
A over C. Now I'm going to do something different. I'm going to find the cosine. And I'm going to use the complement of alpha, which is beta. What's the cosine of beta? Yeah? It's A over C. So the sine of alpha came out the same as the cosine of beta. Right, let's try one more. Let's do the tangent of alpha. Sam, what's the tangent of alpha?
A over B.
A over B. All right. Now let's find the cotangent of the complement, or more generally, the cofunction of the complement. So what's the cotangent of beta?
A over B.
It's also A over B. Cotangent is adjacent over opposite. A is adjacent, B is opposite. And we could keep going. There's a bunch of different pairs of these we could do. But the idea is that if you take cofunctions of complements, the answer comes out the same. Cofunctions of complements. Okay? And that's the complementary angle theorem. Cofunctions of complementary angles are equal. So for this theorem to work, there's two criteria. One, you have to have cofunctions. Sine, cosine, tangent, cotangent, or secant, cosecant. One of those three pairs I just said. And the other thing, the arguments have to add up to 90. So let's look at this. The sine of 15. Using the complementary angle theorem, can somebody tell me what the sine of 15 would be the same as? Yeah? Not quite.
Oh, cosine.
The cosine of 75. Sine and cosine are cofunctions. 15 and 75, complements. Okay, so let's see where you might use that. Now, he told me that the sine of 15 is the same as the cosine of 75. I still don't know what the sine of 15 is. And I still don't know what the cosine of 75 is. But I know they're the same. I have the sine of 35 minus the cosine of 55. What would that come out to? Leo?
0.
0. How come?
Because they're equal.
They're equal. Sine, cosine. 35, 55. They add to 90. You're subtracting cofunctions of complementary angles. You're subtracting two things that are equal. So you get 0. If you change 35 to 34, you can't do the problem without a calculator. Okay, so it's a very special example. How about tangent 20 divided by cotangent 70? Sam? It's 1. You're dividing cofunctions of complementary angles. Whenever you divide two things that are equal, you get 1. So this trick works with division and subtraction. How about addition? If you add two things that are the same, do you always get the same answer? No. You get the thing doubled. So it wouldn't really work with addition. How about multiplication? No. Because if you multiply two things that are the same, you get that thing squared. But with subtraction, you would always get 0. With division, you would always get 1. Okay, so take a second and see if you can figure out that one. Cosecant 15. Well, 2 times the cosecant of 15 divided by the secant of 75. Plus 3. Yeah, Sam?
5.
5. The whole trick is not to try to figure out what the cosecant of 15 is. You're not going to be able to figure that out in your head. But the point is that the cosecant of 15 divided by the secant of 75, it basically cancels out and becomes 1. So you're left with 2 times 1 plus 3. Okay, so these kind of problems have to be set up with very specific numbers to make it work. All right, any questions on that? Okay, so that's the first part of 6.5. So we'll stop there. Okay, the homework tonight, most of it's in the book, but there's 2 problems that I want you to do that are not in the book. So make sure you copy that. So on 361, it's 1 to 14, 16 to 20, just the evens, 21 to 24, and I want you to simplify these last 2 problems. Sine 40 over cosine 50, tangent 35 minus cotangent 55. Okay. As a reminder, we will not be having a test this week because of the 2 B weekdays on Monday, Tuesday. So the 3 tests that I have right now, that's going to make up your term 2 test average. This homework assignment will go on term 2. So will tomorrow's homework assignment. So 2 homework assignments left.